It's a pleasure to continue on fuzzy spheres.
Okay. So thanks for coming today. The plan today is that I will start by talking about the generalizations, right? In the last two lectures, I told you how to do this fuzzy sphere regularization, in particularly how to make it work for 3D icing safety. And today I will tell you how to do the generalizations, although in practice, those generalizations might be a little bit harder to study, but in principle, but they're still, but you can still play with it. So I will briefly talk about how to do this Owen-Wilson feature. As you will say, conceptually, it's rather straightforward. So then I will mainly focus on how to do some of those 3D gauge series, in particular Dirac fermions, coupled with the SU2 gauge field. So, and if time allows, I will talk about conformal defect. You may say that I actually swapped the order of those two in my original plan. Okay, so let me give you a quick recap about what this fuzzy sphere regularization is. So what we are considering is some quantum mechanical model that I have fermions moving on the sphere. And in particular, I'm putting a monopole with flux 4 pi s in the center of the sphere, then, which can be captured by this some connected term and whose eigen energies will be just quantized lambda levels with a gap. And then I can also add some interactions that I like. Those interactions plays a role for realizing phases and also CFTs that we want to study. And in particular, we are going to consider a regime that the kinetic energy is much, much larger than the interaction energy, such that I can just project the entire system into the lowest lambda levels. That's why we end up with a fuzzy sphere. So pictorially, there are different ways of view those lambda orbitals on the lowest lambda level. One way is that you really, you can write down the lambda orbitals wave function, just the so-called monopole harmonics. And if you write it down, plot it, you will realize that those monopole harmonics are Gaussian localized at different latitudes, as I draw here. So then in this, so the Hamiltonian will be written in the orbital space. You can just, let's say, naively view those orbitals as some lattice site with label running from -s to s, and in total they are 2s plus 1 orbitals. And then the model is really just build, is some second quantized Hamiltonian on this 2s plus 1 site. So, and to get the Hamiltonian, you just need to do one thing, which might be tedious, is that you use this formula that tells you that for any electron operators, how do you write it in terms of this second quantized fermion operators that I could say. Then you just plug in this into the interaction, then do some integrals involving spherical monopole harmonics. You end up with some second quantized Hamiltonian, which involves 3J symbols in general. Okay, that's how this fuzzy sphere regularization work. So now, let me. Now let's go to this question that how do we realize the phase transitions or CFTs that we want to study? So for Wilson-Fisher type of CFT, a good way is that first. So it's a phase transition describe the. It's a phase transition between some symmetry breaking state and some symmetry preserving state, right? Then the first question you can ask is that, how do I get those two phases on the fuzzy sphere, right? So remember that in the Ising story, right, the model that we have is, I'm going to just use psi instead of psi to represent those fermions. So the model that we have is like we have two flavors of fermions, and this the spin up and spin down degree of freedom are really just the Ising spin Z2 And then we know that one phase is the symmetry breaking state. You can write down a state which is very simple. Is really just a product state that I have all the electron. So on each orbital, I have 1 electrons, right? And the spin would point either to plus direction or to the minus direction, right? Then I get the 2 ground state of my symmetry breaking state, the Z2, the Ising order state, right? And the disorder phase is just a state that I have spins pointing towards the x direction, which is just, again, a product state that on each orbital I'm still occupying 1 fermions, but this time I want the direction of the spin pointing to x. That's the 2 state that we can have, right? So clearly, the state spontaneous break the Z2 symmetry, this doesn't, right? And then that's just asked that how do I get a Hamiltonian to realize each phase individually, and then I just connect those 2, right? And for this disorder phase, the answer is pretty easy, right? You just write a term like this, then is some sort of transverse term field, then you can realize it as a ground state. So maybe I should put minus sign here. So that's the term that you can realize a disordered phase. For ordered phase, it may not be that intuitive, but you can kind of imagine that if I have some Ising interactions, like SZ, or NZ, it will eventually give me this. And then it turns out to be the case in many different setups. If you just play with some Hamiltonians with density interactions, you will end up with a symmetry breaking state. So that's how we get the, so then we can write down Hamiltonian before the projection. That's really just something like this. Before projection, that's really just some interaction like this. Then you project it using this formula. Then you get some second quantized Hamiltonian, right? You connect those 2 Hamiltonians. You add those 2 Hamiltonians together. Then with a tuning parameter, let's say h, then you can realize 2 phases individually. Depends on the strength of this edge, and in between you will realize a phase transition. That's how things work. So now let's try to do something slightly more complicated. Let's say we want O3 Wilson fission, right? How do we do it? Right. So first of all, you do need O3 symmetry in your model, right? Just like I need Ising symmetry in my model, right? So so for Ising, I place with 2 flavors of fermions, right? Whose maximal flavor symmetry can be O3 or SU2. Then it's natural to ask, okay, then just with this setup, now I'm playing with an SU2 invariant Hamiltonian. Can I realize O3 Wilson fission? So I think the answer is no, but I think the answer is no because this model actually has an anomaly which forbids the O3 Wilson fisher, because we know O3 Wilson fisher doesn't have an anomaly. But for Ising, if you break the O3 down to the Ising, then the anomaly is gone. Right? So instead of thinking about those formal anomalies, let's just do some very poor man's way of thinking. Now let's just follow this logic. Now let's try to construct state that, in particular, let's say if we have two flavors of fermions, can I realize a disorder phase that preserves the entire O3 symmetry? But then you will find that, so here I'm just writing down a product state, right, that has each, the fermions on each orbitals pointing to the x direction, right? That preserves the O2 symmetry, preserves the C2 symmetry, but you say it has a preferred direction that it then breaks the O3 symmetry, right? It's not a symmetric state. So in general, if you let's say if I have 1 electrons in each orbital, then there's no chance that you can create. Let's say we want to consider some product state, then there's no chance that you can get a symmetric product state with 1 electrons per orbital, right? It has to point some direction. So that you realize it's I cannot. So this simple way of thinking is not working. Now, what if I just, let's say, on each side, I'm putting 2 electrons, right? Then I can let it form singlet, right? But then in the end, what you have to do is that I have to leave some orbitals empty, right? Because I don't have enough electrons to put in my system. Then by doing this, you can realize a SO3 invariant state, but SU2, let me call it SU2. I don't want to confuse it with the SO3 sphere rotation. So we can end up with a SU2 flavor singlet, but then if you think a little bit harder, you will realize that, okay, this state indeed breaks my sphere SO3 symmetry, right? Because you know that those orbitals actually forms SO3 irreducible representations, right? If I just choose to fill some of them, then I may end up with SO3 sphere rotation breaking state. That's also something we don't want, right? Because we want to study CFTs that with SO3 symmetry preserving, right? Then this way of thinking, such state won't really do the job as it breaks the sphere SO3 symmetry, right? That's a manifestation of the existence of quantum anomaly in this system. To people who are familiar with condensed matter literature, it's something similar to the LSM anomaly, called Lipschitz-Matthias anomaly on the lattice systems. Okay, so now what we are going to do. So the thing that we can do is now we increase the flavors of those fermions, right? We don't play with 2 flavors. Now let's play with 4 flavors, right? And now let's say I have fermions.
Yeah, question. Okay. Could you just remind me why half filling was important to begin with? Why couldn't you solve it by just filling all the orbitals?
Yeah, so the half filling condition, on the one hand, give me a gap, a state that the charge degree of freedom is gapped, right? And in this case, you can also think, okay, if you change the filling factor, if you add 1 more electron or 2 more electrons or remove some electrons, it will not give you a symmetric state either, right? You have to fill all the states, right?
Yeah, and what if you fill all the states?
Then you just get a trivial gap state, right?
Okay.
Then there's nothing you can tune to get other phases or phase transitions.
Right, thanks.
Yeah. So now let's say we play with a slightly more complicated model that I have 4 flavors. Let's say I add another indices that I goes from 1 to 2, and sigma is spin up and spin down, right? Now this sigma is still the carries the SU2 spin rotation that I want for the O3 Wilson Fisher. Those degree of freedom, this I called I, is just an auxiliary degree of freedom that helps me to realize this state. So now, again, I'm at half filling. That means on each orbitals, now I'm allowed to put 2 fermions, right? Because I have 4 to start with. Now what I can have is at each orbitals, I'm just forming spins, this SU2 singlet, and I occupy all the orbitals and so on. Then I end up with a state that is disordered under the O3 Wilson-Fisher. That's how we can make things work. So then for this guy, you can write down the various different types of Hamiltonian to realize state in a very similar manner as this guy, right? Right. So you can add terms that breaks this I down to some. You can break the symmetry.
The Hamiltonian, I don't understand the state because you show spin up, spin down, but each one of these electrons also has the I quantum number.
Good. So the state, let me write it down explicitly. The state is just a singlet. I think I need this. Right. It's a singlet of my SO3 spin. That's the state look like, right? I anti-symmetrize the flavor indices, which will, symmetrize this I indices, right? That's the state we have, right? So then with this state, you can ask which Hamiltonian can give you, right? There are few various of different choices. It's probably, minus I, thanks. I'm bad at undergraduate quantum mechanics. Okay, thank you. So that's a state we have. Okay, so now you can write Hamiltonians that say have this as a ground state. I think this Hamiltonian might do the job. Some Hamiltonian like this, right? Tau is the indices. Tau is tau x on the indices x on I space. I think this Hamiltonian might do the job. You can also come up with other Hamiltonians and so on to realize this as a ground state. Then you add this type of Hamiltonian together with this type of Hamiltonian that gives you the SO3 symmetry breaking state. Then you can, and then by tuning the strengths, let's say, of this guy, you may realize O3 Wilson-Fisher phase transitions in a very similar manner as the Eisen that I discussed in the last 2 lectures. So similarly, you can do for this, you can realize O2, let's say, just on top of this model, you break down the O3 symmetry down to O2, then you would naturally expect O2 Wilson-Fisher. There may be there indeed some more clever way of doing O2. I think it will be reported on an upcoming paper by Andreas Lochley. So, but the philosophy of getting those transitions is really just first think about the states. How do you get different states? One is symmetry breaking state. That is usually very easy. Will just be given by such density-density interactions. And the other is how do you get the symmetry preserving state, right? There are some anomaly constraints. If you are a very formal guy, you may try to figure out the anomaly at the beginning, then can give you a very good guiding principle about what's the minimal setup to play with. But if you don't want to play with those anomaly, then let's say you just think about for which setup can I get a product state that preserves all the symmetry, then that should be a right setup to play with. So that's more or less like what I want to say about Wilson-Fisher.
Question?
Yeah.
Can you realize any symmetry group at all, like taking into account the anomaly with fermions? Is this a theorem?
You mean by any symmetry group?
Yeah, so if I give you, like I would like to study CFTs which have this symmetry group, and it's always realizable by adding enough flavors of fermions?
Yeah, for symmetry, you can always do that, right?
Including anomaly, including canceling anomaly.
Yeah, that is unclear. That is unclear. But for Wilson-Fisher, you can always get for Wilson-Fisher, I believe we can always do so because Wilson-Fisher doesn't have anomaly. Then you can play with some setup that starts with very large symmetry and then you break it down such that you kill all the anomaly. The difficult part is that, let's say I want to realize CFT with some specific type of anomaly and symmetry. Then can you realize it using fuzzy sphere? Because for that, you need to also get the anomaly right. It's a non-trivial anomaly. Then it's unclear whether you can do it for any CFT. So to be honest, I don't fully understand the anomaly on fuzzy sphere. So we should first understand that part. We only understand it in a few cases that what's the anomaly look like and so on. But we don't have a general understanding. Okay, so that's all I want to say about Wilson-Fisher. Is there any question regarding this part?
Did you also do nomadics with this one?
We tried a little bit, but it's not as good as the icing, but it still say the Wilson-Fisher. We didn't try very hard, so then we plan to play with this later, to say how good it is. The O2 one, according to what Andreas told me, it looks pretty good. Yeah. Okay, that's the Wilson-Fisher. Now let's move to something more interesting, that is 3D gauge series. So the gauge theory I'm going to consider as Dirac fermions coupled with certain gauge field. And I want to first say that the way we realize it is not putting gauge fields on the fuzzy sphere. Instead, we are using more condensed matter mindset that we play with some interacting models, and then in the end, in the IR, it realizes some universality which falls in the same universality as the 3D gauge series. That's how that's the approach we will take. Okay, so to understand this story, I think it would be nice to actually start with something that we are pretty familiar with, is 2D CFTs, and in particular, what I'm going to start with is 2D West-Zumino-Witten CFTs. So as you will say, on the fuzzy sphere, the way that we realize 3D gauge series is actually closely related to this. You can view it as some 3D version of West-Zumino-Witten models. So I think everyone should know West-Zumino-Witten CFTs. So there are various different types of way of describing it, right? And one way that closely related to what I'm going to talk about in 3D is that is this so-called nonlinear sigma models, right? I have some field. I should use different notation. Okay, let me use G here. So I have some. Let's say I have some matrix field. choose. I have some matrix field that I call G, and the matrix field lives on some manifold, right? Which is for the simplest Westermann-Witten models, that will be just some Lie group, right? Like SUN, SPN, blah blah, right? That's the matrix. So we can have a matrix field, and then with this matrix field, we can write down its kinetic term, right? So that's the kinetic term for the nonlinear signal models. A here is just some coupling constant that describe the model, right? And I can have a topological term called Westermann-Witten term, right? I don't need to write it down. I believe everyone here should know what Westermann term is, right? So, and we know that the Westermann-Witten term comes from the, is defined in one dimension or higher, and it comes, let me call this generally as Gn, just as my Lie group manifold, right? We know the pi 3 of the Lie group is Z, and pi 2 is trivial, and then that's why you can extend the space in one dimension higher and then write down topological term. That is the Westermann-Witten term. Okay, and we know that the non-trivial physics comes from the Westermann-Witten term, right? And due to the Westermann-Witten term, so you know that, so at A equal to 0, you can write down the RG flow of the coupling constant, right? At Z equal to 0, you get a Gaussian, right? And which is a thick theory. And then find the coupling. The coupling A is relevant, and it will drive the theory to some strongly interacting fixed point, right? And without Westermann-Witten term, then you will end up with some trivial gap state, trivial vacuum. But with Westermann-Witten term, then you end up with this Westermann-Witten CFT, right? So that's a story for the Westermann-Witten CFT. And the key point for the and the key point for this to happen is really this Westermann-Witten term, right? You can solve this model as what Witten did decades ago, that you can show that this nonlinear signal model really have this conformal fixed point that is Westermann-Witten fixed point. And you can also understand this phase diagram without solving it, just by realizing that due to the Westermann-Witten term, this model has an anomaly, right? And the anomaly can be described by so you know, all the anomaly can be described by some topological partition functions in a one-dimensional higher. And in this case, the anomaly is really just the Chern-Simons term can be described by the Chern-Simons term, like Gn level K Chern-Simons in the 3D bulk. So, and you do have this anomaly, right? So then we know anomaly is an RG invariant quantity. That means no matter what you realize in the IR, or no matter how you do in your models, it has to saturate that anomaly, right? And in 2D, there are few ways. There are not that many ways for you to saturate the anomaly. One way is that is a CFT. Indeed, there's only one way to saturate this anomaly. That is a conformal field theory, right? So usually in higher dimensions, you can saturate the anomaly using a non-trivial topological quantum field series. But in 2D, we don't have such non-trivial topological quantum field series. There's also another way to saturate an anomaly. That is, you can spontaneously break the global symmetry, which in 2D is not an option due to this so-called Mermin-Wagner theorem. You cannot spontaneously break any non-abelian group or continuous group. Yeah. So so then with anomaly, and then you know, okay, there has to be a CFT there, right? That's a perspective from anomaly. Right? That is also important for the later part of the generalization. Right? In some sense, this CFT is a symmetry enforced or anomaly enforced CFT. Okay, and before we go to 3 dimensions, I would like to also say a little bit about this Wilson Fisher. There's a new in this old story. Actually, there's a new narrative about a new way of you thinking about those Westermann-Witten safeties, and I think the paper discussing this was one of the papers. The pioneer papers was from my colleague, John Gomez, and his student. So the story is that for those Westermann-Witten safeties we are familiar with, indeed they have a gauge theory descriptions. That's really just critical gauge series that with Dirac fermions coupled with a gauge field. In particular, you can write down a dictionary. So in 2D, you can. I think they proved this because I think mainly because in 2D the RG flow is very strict due to the anomaly and so on, right? So you can really prove this. So, for example, if you have SON level K Westermann-Witten safety, it corresponds to n flavors of Dirac fermion coupled with an SOK gauge field. So here the Westermann-Witten level goes to the rank of the gauge group. So you can easily check that this duality passed a lot of sanity check. For example, the global symmetry is the same, right? We know the Westermann-Witten safety has a SUN left and SUN right. That's also the case for this gauge series. And you can also show that anomaly is the same. And if I consider SPN level K, what I need is an SPK gauge field. And for SUN level K, there's a swap that you do want to consider UK gauge field instead of SUK gauge field. And for UN level K, what you want to consider is a SUK gauge field. So yeah, this swap can also easily understood by looking at the symmetries, right? So that is the way that I mean this is a new way to think about those familiar Westermann-Witten safeties, right? So now now what we are going to do is that we go to 1 dimension higher, right? And the target are still gauge series, right? Dirac fermions coupled with certain gauge field. But now what we want to realize it is using models of Westermann-Witten models instead of I directly put a gauge field there. But you know that we know that the Westermann-Witten models or nonlinear signal models is non-renormalizable in 3D. So you cannot really do QFT for this model. It's not really well defined. But in our approach, this we consider some interacting models. It's not QFT at all. So there's no trouble for us. And what we really want to do is that realize a model with the exact same global symmetry and also anomaly as these nonlinear signal models in 3D. That's the strategy that we are going to take. All right, so now maybe I can still use here. This is a phase diagram of the 2D Westermann-Witten model. Right. Now let's move to 3D. Let's say we have. So again, we have some nonlinear signal models in 3D defined on certain target space. Right. That target space should have a non-trivial pi4. Let me just call it. How should I? let me call this target space as M, fancy M, and it should have a non-trivial pi4, and it should have a trivial pi3. Right? There are a bunch of such manifold satisfying this relation, and for example, you can consider Grassmannian, then which I will be focused on in this lecture. It satisfies this homotopy. So now in 3D, then we ask if we have such nonlinear signal models in 3D, what would if I'm able to define it with certain regularizations and so on, right? Then what kind of phase diagram should we expect, right? So then the first thing that you know is in 3D, now spontaneous symmetry breaking is an option, right? And what we are going to happen is for nonlinear signal models at small couplings, it realizes a symmetry breaking state, right? And the symmetry breaking state will have its manifold precisely to be the manifold of my target space, and that's what nonlinear signal model is used for, right? To describe some Goldstone phase and so on in high dimensions, right? And you could imagine a situation that now if I increase my coupling, then the symmetry breaking state might be disordered. I may recover the symmetry, right? Then there will be a symmetry order disorder transition, right? And beyond which it will flow to some interacting fixed point, right? And for this scenario, it's really if you try to for some cases you can indeed try to connect 2D with 3D, for example, do a 2 plus epsilon expansion where you really say that the symmetry breaking fixed point and the order disordered fixed point gets merged to the Gaussian in 2D, right?
This second diagram, is it with Westermann-Witten term or without Westermann-Witten term?
For this part,
yeah,
it's without Westermann-Witten term. Yeah, let's not draw this first. Yeah, let's leave this part empty for the moment.
Yeah. That's what I was.
Yeah, thanks for the question. Yeah. So for generally for any nonlinear signal model, you would expect such case, such scenario that I do get symmetry breaking and some order disorder transition. And if you go to 2D, then those two fixed point merge, right? And you can even do 2 plus epsilon expansions to understand the physics of this order disorder phase transitions. And the famous 2 plus epsilon expansion of Owen Wilson Fisher is actually done in this way, where you can really show the existence of this fixed point, and in 3D, that's the Wilson Fisher that we are familiar with. Okay, so now let's ask, what if you have a topological term, right? So then the conjecture is, if you have this Westermann-Witten term, I will still have this non-trivial CFT fixed point, and some of those CFT fixed point will be gauge series if you choose the manifold to be the Grassmannian.
But now you have 2 fixed points, so are they both CFTs?
Yeah, they are both CFTs. Yeah.
And is the one on the left, it's still the usual, the same one that you had without Westermann-Witten term, or are they both of a different kind?
They both become different.
Different, okay.
Yeah. Because those two CFTs should have the same anomaly. So once you have Westermann-Witten term, in particular if the Westermann-Witten level is 1, it has a non-trivial anomaly, which has been understood for certain situation. It has been understood in the context, in the literature. So and then it's pretty similar as the argument that anomaly argument that I gave in the 2D case. We know the global symmetry of the model. We know anomaly of the model, right? Then if I have a fixed point that does not spontaneous break symmetry, then that fixed point has to be has to be either topology ordered or be a conformal fixed point. And in some situations, the anomaly may not be able to be saturated by a top TQFT. And in literature, that was called symmetry-enforced gaplessness. I think it was first discovered by Chong Wang and Santo. I don't remember which year. It was Chong's PhD time. So, and it turns out that for the Grassmannian that I'm going to talk about, it also falls in the so-called symmetry-enforced gaplessness. And that means if the global symmetry, both flavor and the parity symmetry is preserved, then it has to be a conformal field theory. So, and comparing those two phase diagrams, so the naive picture is really just when you go to 3D, this Gaussian fixed point gets splits into two fixed points, one order disordered fixed point, but this IR conformal fixed point is just it's still there. Nothing could destroy it. On this, in some situations, you will say that those two fixed points could merge and collide into the complex plane, which I will also talk about a little bit later. And then those two fixed points will disappear together. So, except for that, then you would expect there's a non-trivial conformal fixed point for this 3D Weissenberg-Witten FTs. All right, so now let's move to the 3D. That's I think let me talk a bit more about 3D situation. In particular, I want to just follow the story of 2D that I know in 2D those Weissenberg-Witten FTs are really just gauge series that has Dirac fermions coupled with the SOK with some gauge field. And in 3D, so I want to play with the nonlinear single models with Weissenberg-Witten term. And in particular, I'm going to play with the Grassmannian, the nonlinear single models with the target space to be the Grassmannian.
Sorry, can I ask a question about this 2D gauge theory description? I'm a bit confused about here. So the n size, the first line, how does it couple to SOK gauge field?
They are the fundamental of the gauge field.
So you have n size in the fundamental.
Yeah. All of those are fundamental. Yeah, I should be more concrete on that. Yeah, fundamental.
And you should the infrared fixed point is equivalent to the WZ model. That's a statement.
Yeah.
Because usually I would have thought that the infrared fixed point is a cosine model because, but you say the cosine model somehow itself is equivalent to WZ model.
Yeah. You can think it that way. Yeah. I think in their paper they also discussed that. Indeed, for any minimal models or any cosine models, you can write down a gauge theory description for that, which sometimes can get very complicated. Yeah. Okay, so in 3D, what I'm going to consider are the so-called Grassmannian, and just in parallel with this story, right? Let's say if I want to realize SOK gauge field, and the Grassmannian that I will have is the SON Grassmannian. And Weissenberg-Witten, and that will give me the 2N flavors in fundamental. Let me write it more explicit, that fundamental fermions coupled with SOK gauge field. It's really in parallel of 2D story, except that now we need to play with Grassmannian. One reason is for Lie group, you don't have this non-trivial topology. Because for Lie group, pi3 is non-trivial, so then you cannot define a Weissenberg-Witten term, right? And for Grassmannian, it turns out that it just satisfies this condition. that pi 4 is non-trivial and pi 3 is trivial. And you can kind of say why in 3D you need Grassmannian instead of Lie group is from the symmetry, right? We know that for this gauge theory, the global symmetry is SO2n. There's also maybe magnetic Z2 and magnetic Z2. And for this guy, if you look at the symmetry, it's indeed SO2n, right? If you play with Lie group, then you get SO2n times SO2n, which won't give you a correct global symmetry. But for this Grassmannian, it is. And you can also recover the, I think it also have a Z2 symmetry. And yeah, coming from the pi 2 of this is a topological Z2 in Grassmannian that corresponds to the flavored Z2 of the SOK gauge series. Right? And you can further show the anomaly is the same. I think that's probably, for the anomaly aspect, it was probably first discovered by, studied by the paper by Zohar Komogowski and Nati Seiberg. They studied the symmetry breaking of the QCD3, and then they find those nonlinear single models there. Okay, so that is for the SOK gauge field. Then the rest of the theories.
Can I ask a quick question?
Yeah.
Did you say why you decided to go through this path and not to just try to write an Hamiltonian for the right-hand side directly?
I don't know how to put gauge field in the fuzzy sphere. There may be a way to do so. I don't know.
Certainly, yes. There are papers by.
Yeah. But that's non-commutative field theory.
Absolutely, it's non-commutative field theory.
Yeah.
So, since everybody keeps mentioning this as the boogeyman, can somebody explain why don't we want?
I'm not the right person to comment on.
No, me neither. But you mentioned several times this issue of UV-IR of decoupling. So I think it has been shown. I don't know that there is a complete conceptual understanding, but it has been shown that if the fields that you want to realize your model with, like the fundamental fields that really describe the physics, are non-commutative, then as you remove this cutoff, you don't get back what you expect. There is some you end in a different universality class.
So other things, for other gauge theory or Grassmannian, this correspondence is really just in parallel with 2D, that if I have SU, then I end up with a UK gauge field. If I have U, I end up with is a SUK gauge field, right? That's the correspondence. Then you can pick up your favorite gauge theory and then ask, how do I realize these nonlinear signal models, particularly on the fuzzy sphere? So for this duality, for this correspondence, you can quickly go through some sanity check that's looking at the global symmetry to say whether it's recovered. For example, for UK gauge theory, you know that the global symmetry is SU2n, and there's a topological U1 symmetry. And the way it realizes symmetry is that this target space has exactly that symmetry as SU2n and U1. And for the SUK gauge theory, you know there's an SU2n flavor symmetry and a U1 phase rotation. And this symmetry, the SU2n is realized as a global symmetry of this target space, but the U1 is realized in a very funny way. That is a topological U1, because this Grassmannian has a non-trivial pi 2. So then you can define a topological U1 symmetry. And this topological U1 symmetry turns out to be just the U1 phase rotation of this gauge series. And due to the Westrup-Nowitton term, indeed, Zohar-Komogolsky and Knighty-Seiberg, they show that due to the Westrup-Nowitton term, then if you have the statistics of this skyrmion, of this pi2, is actually fermion or boson, depending on the number of the k, level k, to be even or odd or even. And this, again, recovers the structure of this gauge series.
Sorry, looking at the first line, if I just look at the case n equals 2, that's topologically S2 times S2, right? I mean, why is pi 3 equals 0?
I mean, this one?
Yeah. Does it work in case n equals 2, or is there some restriction on
Yeah,
n?
there may be some exceptions for small n.
Okay. And another thing I just want to make sure about this story of the 3D Westrup-Nowitton terms. You say the condition for this to be well defined is just pi 3 equals 0 and pi 4 equals z. But naively, that means, okay, you can define this on the 3 sphere, but on other 3 manifolds, there might be some further subtlety. If I recall,
Okay.
there was a paper by Komogolsky, Fried, and Seiberg that discussed, not quite for this, but some, right? There's
You're
some.
talking about like H4? I need H4?
No, they were talking about a case where it's not quite this, because they had a case where pi 3 is z is equal to 0, but still, I had the impression that going beyond 2 dimensions, it's not quite enough to consider just the homotopy group. You have to consider the actual homotopy class of mapping from the generic space-time manifold to the target space.
I know there are some subtleties, but not, yeah.
But you say in this case,
In this case,
you don't
yeah,
expect.
it's well defined, right? I think the people you mentioned discuss this case. You can have Westrup-Nowitton term. Okay, so we can. Then from the gauge series side, we kind of know what should happen, right? For example, for the phase diagram that I draw here, we kind of know what the phase diagram look like for gauge series, right? So for all those gauge series, we know that if I have this, my flavor is much larger than my rank, then I really get, I can get a non-trivial conformal fixed point that is the that is this gauge theory will have a non-trivial conformal fixed point. That is the CFT fixed point. Attractive CFT fixed point I drew previously, and the transition between them will be could be some gauge series. Those gauge series coupled with Gaussian-Uyukawa field, then it will describe the transition between them. Okay, so and we know another situation that when my rank is much larger than than my flavor group, then I will end up with the gauge theory. Just don't flow to a conformal fixed point, right? And then we know for gauge theory, we know the phase diagram is really, I just have spontaneous symmetry breaking fixed point left for gauge series, also the case for nonlinear single models, and we know the gauge theory will flow to the symmetry breaking, right? And from gauge theory side, if this happens, then the spontaneous symmetry breaking state should have its ground state manifold on those Grassmannia, right? I think that's really just the so-called Vafa-Witten theorem that proves that. This phase diagram indeed gives another justification that why you want to expect that such Westrup-Nowitton models where on those target space are related to the gauge series. And for the existence of Westrup-Nowitton paper, also Westrup-Nowitton term that was shown by Komogolsky and Seiberg for those critical gauge series. And we know those two cases, and we kind of know that when you goes from large flavor to small flavor, what will happen is that those two fixed points will approach to each other, and eventually at n equal to nc, what I have is those two fixed points just merges to a single fixed point, right? And that is at the critical flavor. And that's the boundary of my conformal window of the gauge series. And if I go to smaller n than what happened, okay, that me. Yeah, if I go to a smaller flavor, then it's what really happened is that those two fixed points just collide into the complex plane that we get the complex fixed point as discussed by Slava and collaborators. So yeah, that's the scenario. You can say this scenario is really, for the both sides, is also kind of consistent, whereas, yeah. And then the idea is that we want to realize those such nonlinear signal model with rational weighting term and using fuzzy sphere, and that would mimic. So then for that model, I tune some interactions. I may realize one of those phase diagrams depending on the UV setup. And for that, I can also explore the physics, like what's the conformal window of the theory, right? If I find large flow like this, then we know it's not conformal. If we find a situation like this, we find two conformal fixed points, then we know that it lies in the conformal window and we get the critical gauge series and so on. That's what we want to do. All right, so I think I only have 15 minutes left. So, so now let's go to the fuzzy sphere. So the one nice thing about the fuzzy sphere is, or I should say that this lambda level stuff is that it's actually a very natural way to realize those nonlinear signal models with rational weighting term. It's indeed more natural than those Wilson-Fisher Eisenstein.
Sorry, can I ask a question?
Yeah.
Is there a generalization of this story for 4 dimensions?
Yeah. I think, yeah, for 4D, then you play with the Lie group, right? I think people using nonlinear signal model with rational weighting term to describe the chirosymmetry breaking phase of the gauge series. Last week there was a talk on this, I think. At least I remember.
But what about the fuzzy sphere part? That's going to be harder, right?
Yeah. Then you need to play with, fuzzy sphere. It exists, but it's much more tricky.
Why is this tricky?
Yeah, because the fuzzy sphere is related to lambda levels, and on the formal side, it's related to the Chern-Simons term, right? And we know Chern-Simons term only exists in odd space-time dimension, right? That is 2 plus 1D or 4 plus 1D, right? For 3 plus 1D, you don't have that. But there's a way to still realize fuzzy sphere. The idea is that you start with 4 plus 1D and then compactify it to 3 plus 1D. I think mathematicians discussed that, and there's also some physicists studied quantum Hall state in this setup. But I think, it's more complicated, and I don't really understand this, how the details work there. Okay, so now
I just want to make sure I didn't miss the setup at the beginning. You're still on the sphere with the magnetic field. You're on top of it, and you have the same half-filling story. And then, so when you say that you know this Hamilton described the Grassmannian Sigma model, I mean, what's the level of rigor in which that is established? Okay.
But it's an interactive model, that's all you can add. Whether it's realized that the fixed point we want, then we want to study using some other ways. But the kinematics, like symmetry and anomaly, that's something.
But this statement is all within the context with this magnetic field. So okay. Thanks.
Sorry, it was a bit too fast for me. So is the claim that choosing 2n fermions or 2n orbitals to occupy out of this 4n, the way to choose is parameterized by this Grassmannian? Is that the claim? Or what? So I couldn't follow exactly this argument here. I'm trying to understand if what you mean here is that since you are at half-filling, you have to choose 2n out of the 4n to occupy, and the way to choose that is parameterized by the Grassmannian, by a point in the Grassmannian. Okay. Is there a way to write the actual state? So you have to choose like 2n out of those indices and 2n creation operators, right, acting on the vacuum. So you have 2n indices. How does that relate to this matrix A that you are claiming here?
Let's say you can have a state that have a versus to a field, then you can have A here, then you will relate to some other information.
Okay, thank you. Thank you.
So then
Okay, by Q here, you probably just mean fermion bilinears, or well, acting on the vacuum. Is that what you mean? By Q. Okay, thank you.
so the Western law wouldn't have
In the interaction Hamiltonian, the relative coefficient between the two terms, is that important? And how do you, is that to cancel some ground state energy or something?
I mean, naively, that's really corresponds to this half incidence of my models.
Sorry, can you explain? So if I change the coefficients, relative coefficient, what happens? What goes wrong? Like the two terms, right? I mean, if I multiply the second term by a factor of 2, what goes wrong? Yeah. I mean, what no, between this term and the previous. Yeah, the relative coefficient, normalization between these two terms. Oh, those are u and v. Those are different functions. Sorry. Sorry, you say the u and v, what's the relation between u? So you had to tune that? I see. I see.
Sorry, one more question. What changes in the story of the Wessel-Witten term? So how would you change the Hamiltonian to get level k instead of level 1? Because at level 1, it looks like your the last in the table is already fulfilled. Like you have U4n divided by U2n, U2n, which is 4n psi fundamental without gauge field because I see 1. So like, is it easy to upgrade?
Questions?
So in the story of distinguishing complex fixed points from real fixed points and so on, it's important to make sure that you are not confusing the complex fixed point scenario from large corrections to scaling due to almost marginal operators, which you expect to have when you are near the fixed point annihilation. So how in your paper did you distinguish the two scenarios?
Yeah, so there are multiple things can be done, and one thing, the major evidence for us is that what we find we have scaling dimension of the singlet, because we have a good approximate conformal symmetry, then we can just read out the scaling dimension. And then what we find is that, say, as I change the system size, right, which we call an orbital, to S+1, what we find is that for small system size, we find the lowest singlet is slightly larger than 3, which means it's slightly irrelevant. And what we find is as I increase the system size, I find it becomes slightly irrelevant below 3. So, and this observation can be like, I mean, it's really just carrying a flow like this, right? Let's say I'm starting with someplace here, and then first the flow is attractive, being attracting to the adjacent or complex fixed point. And that's why initially the noise singlet is irrelevant, slightly irrelevant. But then when I hit here, you know the singlet is relevant, such that I introduce the data of the complex fixed point. So in other words, we say the singlet flowing from irrelevant to relevant, that is a flow that can be understood using for this complex fixed point. But for all other scenarios, that will not happen. However, it doesn't mean that it could be that there could be a situation that just due to fine size correction that the scaling dimensions of singlet just is somewhat non-monotonic with system size. Then if that's the case, that's possible, but we don't find any indication of that.
No, it was monotonic. It was monotonically decreasing or increasing with the system size.
Yeah. It could be non-monotonic, right? The thing is, we don't see any signature in our data for this one.
It's kind of surprising because in previous simulations of this model, people found that the correlation length of this model is really huge. I mean, it was like, well, in some units, it was several hundred lattice spacing. While, yeah, so it would be surprising if you really, in your relatively small system sizes, if you could really approach this point and go through it. So, which is needed to interpret your scenario. Okay.
So this is probably a very naive question. So last time when you, for the Ising, the interaction Hamiltonian, you had the U of R times NZ, sorry, N0, N0 minus NZ, NZ, right? That's what you were last time. That looks a little similar to this, except that here you have U and V, where previously you just have a U and the two coefficients are reticle or fixed. Well, what's the reason for, in the Ising case, that you had the... Okay, but A priori you could have chosen the two coefficients to be different. I see. Okay.
For this model, that's somehow saying the setup is maybe more natural for this story. Because here I'm really playing with the minimal interaction that I should have, then it works. For easing, that's not the case.
Okay, so if there are no more questions, let's thank Chen for a very nice mini course. And since